Stray current corrosion happens when stray electrical current flows through metallic structures from external sources. This flow causes electrochemical reactions that damage the metal. Several factors can lead to this. Firstly, grounding issues with electrical systems or nearby equipment can be a major cause. Secondly, electrolysis from cathodic protection systems, designed to prevent corrosion, can sometimes inadvertently cause it. Thirdly, welding operations can also introduce stray currents. To diagnose and troubleshoot this issue, use a multimeter to measure the electrical potential between the damaged piping and the surrounding soil. A significant difference in potential indicates straight current flow. Check the grounding of the electrical systems, ensuring that all grounding connections are secure and up to code. Inspect cathodic protection systems for leaks or improper installation, as these systems can unintentionally introduce stray current into other structures. Review the welding history of the area, as welding can create voltage gradients that attract stray current. Once diagnosed, several remediation steps can be taken. Firstly, isolate the stray current source by identifying it and eliminating or mitigating it as much as possible. Secondly, install sacrificial anodes, which corrode preferentially, thus protecting the underground piping. Thirdly, improve the electrical conductivity of the soil by adding conductive materials such as carbon or salt to help dissipate stray current. Fourthly, coat the piping with an insulating material to prevent direct contact between the piping and stray current. There are some additional considerations to keep in mind. Firstly, ensure proper insulation between chilled and hot water piping to prevent the transfer of stray current from one system to the other. Secondly, monitor the piping regularly using a half-cell potential survey or other methods to track the potential difference in corrosion rate. Thirdly, consider using non-metallic piping materials such as polyvinyl chloride or polyethylene piping, as they are less susceptible to stray current corrosion. A qualified electrical engineer or corrosion specialist can provide assistance with diagnosing and remediating stray current corrosion. Implementing a maintenance program to regularly inspect and protect the piping from further damage is crucial. Staying up to date with industry best practices and standards for stray current control is essential for preventing future issues. Understanding the role of variable frequency drives, or VFDs, in this context requires a deeper dive into how they might contribute to stray current. VFD control the speed of the 10 horsepower pumps by varying the frequency and voltage of the electrical supply to the motors. While VFD offer energy savings and precise motor control, they can also introduce harmonic distortion into the electrical system. Harmonics are unwanted high-frequency currents and voltages that can circulate through the grounding system and potentially contribute to stray current. The 480 volts, three-phase power supplied to the pump stepped up from the 120/208 volts service via transformers could also be a factor. Transformers, while generally isolating, can still allow some harmonic currents to pass through, especially if they are not properly grounded or shielded. To mitigate the risk of VFD contributing to stray current, several measures can be implemented. Firstly, install line reactors or harmonic filters at the VFD input to reduce the harmonic distortion injected into the power supply. Secondly, ensure that the VFD are properly grounded according to the manufacturer's recommendations and relevant electrical codes. Use a dedicated equipment grounding conductor from the VFD to the main grounding electrode system. Thirdly, consider using shielded power cables for the motor connections to minimize the radiation of electromagnetic interference, which can also contribute to stray current. Fourthly, perform a power quality analysis to measure the harmonic content in the electrical system. This analysis can help identify specific harmonic frequencies that may be contributing to the corrosion problem. Regarding the grounding system, it is crucial to ensure that it is robust and effective in providing a low impedance path for fault currents. Verify that the grounding electrode system, consisting of ground rods, ground plates, or underground metallic water pipes, is properly installed and connected. Check the resistance to ground of the grounding electrode system to ensure that it meets the requirements of the National Electrical Code, or NEC. Supplement the grounding electrode system with additional ground rods if necessary to reduce the resistance to ground. Bonding is another critical aspect of the grounding system. All metallic components, including the chilled water piping, hot water piping, electrical conduit, and equipment enclosures, should be properly bonded together to create an equipotential plane. This helps to minimize voltage differences between different parts of the system and reduces the likelihood of stray current flowing through the piping. Use bonding jumpers to connect sections of piping together, especially at joints and couplings. Ensure that the bonding jumpers are properly sized and installed according to the NEC. The fact that the chilled water piping is experiencing corrosion while the hot water piping is not may be due to several factors. Firstly, the temperature difference between the two systems can affect the corrosion rate. Chilled water systems typically operate at lower temperatures, which can slow down the corrosion process. However, the lower temperature can also increase the solubility of oxygen in the water, which can accelerate corrosion in certain conditions. Secondly, the water chemistry of the two systems may be different. Chilled water systems often contain additives such as corrosion inhibitors and biocides to prevent corrosion and biological growth. If the concentration of these additives is not properly maintained, the corrosion protection may be compromised. Thirdly, the flow rate of the water in the two systems may be different. High flow rates can increase the rate of corrosion by increasing the supply of oxygen and corrosive agents to the metal surface. The presence of pinhole leaks in the chilled water piping is a common symptom of stray current corrosion. These leaks typically occur at locations where the stray current is concentrated, such as at joints, wells, or areas with damaged insulation. To locate the source of the stray current, a systematic approach is needed. Firstly, perform a visual inspection of the electrical system and the surrounding area to identify any obvious sources of stray current, such as damaged wiring, faulty equipment, or improper grounding connections. Secondly, use a clamp meter to measure the current flowing in the grounding conductors and the piping. This can help to identify the path of the stray current and pinpoint its source. Thirdly, use a ground fault circuit interrupter, or GFCI, tester to check the operation of the GFCIs in the electrical system. GFCIs are designed to detect ground faults and interrupt the circuit to prevent electrical shock. If a GFCI trips frequently, it may indicate a ground fault that is contributing to stray current. Fourthly, perform a soil resistivity test to measure the resistance of the soil to the flow of electrical current. This can help to identify areas where the soil is highly conductive, which may be attracting stray current. To mitigate stray current corrosion, several strategies can be employed. Firstly, electrical isolation can be used to prevent stray current from entering the piping system. This can be achieved by installing insulating flanges or couplings in the piping to break the electrical continuity. Secondly, cathodic protection can be used to protect the piping from corrosion by making it the cathode in an electrochemical cell. This can be achieved by installing sacrificial anodes or impressed current systems. Thirdly, coating the piping with a protective coating can prevent direct contact between the metal and the corrosive environment. This can be achieved by using epoxy coatings, polyurethane coatings, or other types of protective coatings. Fourthly, improving the drainage around the piping can help to reduce the moisture content in the soil, which can slow down the corrosion process. This can be achieved by installing drainage ditches or perforated pipes to remove excess water from the area. Regular monitoring of the piping system is essential to detect and address any signs of corrosion before they become serious. This can be achieved by performing regular visual inspections, ultrasonic thickness testing, and electrochemical measurements. The results of these inspections and tests should be documented and used to develop a maintenance plan to protect the piping from corrosion. When selecting materials for underground piping systems, it is important to consider their resistance to corrosion. Non-metallic materials such as polyvinyl chloride, high-density polyethylene, or fiberglass reinforced plastic are highly resistant to corrosion and are often used in corrosive environments. Metallic materials such as stainless steel, copper, nickel alloys, or titanium are also resistant to corrosion, but they are more expensive than non-metallic materials. When using metallic materials, it is important to select a material that is compatible with the soil conditions and the water chemistry. The use of variable frequency drives with 480 volts, three-phase motors set up from a 120/208 volt service is common, but it can introduce challenges related to harmonic distortion and stray current. To address these challenges, it is important to implement a comprehensive grounding and bonding system, use harmonic mitigation techniques, and regularly monitor the piping system for signs of corrosion. Consulting with a qualified electrical engineer or corrosion specialist is essential to ensure that the piping system is properly protected from stray current corrosion. Understanding the principles of electrochemistry is fundamental to understanding stray current corrosion. Corrosion is an electrochemical process that involves the flow of electrons from a metal to its environment. The metal acts as the anode, where oxidation occurs, and the environment acts as the cathode, where reduction occurs. The flow of electrons creates an electrical current that drives the corrosion process. Stray current corrosion occurs when an external source of electrical current is introduced into the corrosion cell. This external current can accelerate the corrosion process by increasing the flow of electrons from the metal to the environment. The amount of corrosion that occurs is directly proportional to the amount of electrical current that flows. The direction of current flow is also important. Corrosion typically occurs at the point where the current leaves the metal and enters the environment. This is because the metal at this point is acting as the anode, where oxidation occurs. The severity of stray current corrosion depends on several factors, including the magnitude of the stray current, the duration of the exposure, the conductivity of the soil, and the type of metal. Higher stray currents, longer exposure times, more conductive soils, and more susceptible metals will result in more severe corrosion. The difference in potential between the chilled water piping and the surrounding soil is a key indicator of stray current corrosion. This potential difference drives the flow of electrical current, which in turn drives the corrosion process. By measuring the potential difference, it is possible to assess the risk of stray current corrosion and to monitor the effectiveness of corrosion mitigation measures. The use of a half-cell potential survey is a common method for measuring the potential difference between the piping and the soil. This survey involves inserting a reference electrode into the soil and measuring the voltage between the reference electrode and the piping. The readings obtained from the survey can be used to create a potential map of the area, which can help to identify areas where stray current is concentrated. The selection of sacrificial anodes is an important consideration in cathodic protection systems. Sacrificial anodes are made of a metal that is more electrochemically active than the metal being protected. When a sacrificial anode is connected to the piping, it corrodes preferentially, protecting the piping from corrosion. The choice of sacrificial anode material depends on several factors, including the soil conditions, the water chemistry, and the desired life of the anode. Common sacrificial anode materials include zinc, magnesium, and aluminum. The design of impressed current cathodic protection systems is more complex than the design of sacrificial anode systems. Impressed current systems use an external power source to drive the flow of current from an anode to the piping. The anode is typically made of a non-corroding material such as graphite or mixed metal oxide. The power source is used to control the amount of current that flows, which allows for more precise control of the corrosion protection. The location of the anode is also important in impressed current systems. The anode should be located in an area where it can distribute the current evenly over the piping. The installation of insulating joints is a common method for preventing stray current from entering the piping system. Insulating joints are designed to electrically isolate sections of piping from each other. This prevents stray current from flowing through the piping and causing corrosion. Insulating joints are typically installed at points where the piping enters or exits a building, or at points where the piping crosses a boundary between different electrical zones. The inspection of existing piping for signs of stray current corrosion is an important part of a corrosion management program. Visual inspection can reveal signs of corrosion such as pitting, cracking, and metal loss. Ultrasonic thickness testing can be used to measure the thickness of the piping wall and to detect areas where the wall has been thinned by corrosion. Electrochemical measurements can be used to assess the corrosion rate and to monitor the effectiveness of corrosion mitigation measures. The frequency of inspection should be based on the risk of corrosion and the consequences of failure. Piping systems in corrosive environments should be inspected more frequently than piping systems in non-corrosive environments. The consequences of failure should also be considered. Piping systems that carry hazardous material should be inspected more frequently than piping systems that carry non-hazardous materials.